right, so for the last couple of weeks, we've talked about how forces do work on an object and therefore change the energy within the system. And so we've built that up to where we've been working conservation of energy problems. Well, now what we're going to do is we're going to come back and we're going to talk about how those forces act on a particle over time to change something known as the momentum. And so we'll build up to working what are known as conservational momentum problems. So let's start by sort of talking about a definition for momentum. So again, a linear momentum of a particle we can calculate with the following expression. So P here is the linear momentum, M is the mass, V is the velocity vector. So this tells me a couple things. First and foremost, it tells me that momentum is a vector quantity. So really this is three equations. One that tells me that the x component of momentum is equal to the mass times the x component of velocity. A second one that tells me the y component of momentum is equal to mass times the y component of velocity. And then a third one that we won't use very often, but it's still there, is that the z component of the momentum is equal to mass times the z component of velocity. The next thing that this equation tells me is that the momentum vector has to point in the same direction as the velocity vector. And I know this because I'm taking the velocity vector and just multiplying it by mass, which is always a positive scalar. So when I multiply a vector by a positive scalar, I don't do anything to change its direction. So it tells me that the momentum vector has to point in the same direction as the velocity vector. And that'll be useful because usually we'll have a pretty decent sense about what the direction of the velocity vector is. And if we know the direction of the velocity vector, then we also know the direction of the momentum. The third thing this tells me is, again, that I don't have a very good definition in words for what momentum is. And so what we often fall back on is Newton's own words in saying that momentum is a measure of an object's quantity of motion. Now, I don't really know what this means, to be blunt, and we haven't found a better way for describing in words what linear momentum means since Newton said this 300 years ago. So mostly what we do, again, is we recognize that the linear momentum can be calculated with this equation, and that it depends on two things. One is how much stuff there is in the object, what its mass is, and then what its velocity is. So how fast is it going and what direction is it going? And then in terms of units, well, again, if I think about this equation, units of mass are kilograms, units of velocity are meters per second. So this tells me that the units of momentum are kilogram meters per second. So this, even though momentum is a really fundamental quantity, we don't have something else that we write this as. So this is the way that we're going to write out our units for linear momentum. Now, if you want to start talking about how the momentum changes, that's talking about the impulse. So basically, when a force acts on an object, how that force acts to change the object's momentum, again, depends on the magnitude, direction of the force, and the time interval over which it acts. So J here is the impulse. It's equal to the force acting on the object times the time interval that the object acts over. So this is just the force times T final minus T initial. Again, this is a vector equation. So there's really the x component of the impulse is equal to the x component of the force times our time interval. The y component of the impulse is equal to the y component of the force that acts on the object over the time interval. And then the z component of the impulse is equal to the z component of the force times the time interval. Now again, this is true for a constant force. And a lot of forces that we run into aren't constant. So the way to sort of get around that is to say, well, if the force isn't constant, then what we'll be interested in is the impulse generated by the average force acting over that time interval. So instead of dealing with some complicated structure in terms of how that force acts on our object over time, instead what we'll do is say, well, I can treat it as the average force that will act in a constant way over that same time interval. That's also going to give me the impulse. Now, fundamentally, the impulse is really just another way of saying the change in momentum. So the impulse momentum theorem tells us that again, if we have the impulse due to a single force acting on our object, that's going to go to change the object's momentum. If you have multiple forces acting on the object, then this simply becomes J net. So the net impulse is equal to the change in momentum. So fundamentally, this sounds a lot like the work energy theorem, where we said the net work was equal to the change in kinetic energy. The biggest difference here is that the net impulse is equal to the change in momentum is a vector, not a scalar equation. So we've got to deal with it as a vector problem. Now, fundamentally, this is all tied up with Newton's laws. So let's revisit Newton's first law. And what we're going to do is we're going to sort of switch it around a little bit. So objects at rest remain at rest, and objects in motion continue to move in a straight line at a constant speed unless their momentum is changed by a net external force. So we'll emphasize external forces when we talk about them in class, but basically what this tells us is that an unbalanced external force, this simply means external forces that don't cancel themselves out, will change an object's momentum. So if you have a net force that isn't zero, then that's going to act to change the object's momentum. So if the velocity is constant, that means the momentum is constant, which means the momentum doesn't change, which tells you that your net impulse is zero, which tells you that the net force is zero, which tells you that you have no acceleration acting on your object. If, on the other hand, the velocity is changing, then that means the momentum has to be changing, which tells you that you do have a net impulse. The net impulse can't be zero under that case. That also tells you that the net force can't be zero. And then that tells you that your object is accelerating. So, sort of rethinking Newton's first law in terms of momentum is basically saying that if our velocity changes, then our momentum must also be changing. And our momentum changing means that there has to be an impulse from a net external force that's acting to change the momentum. Newton's second law, again, I can rethink about that, or I can think of that in terms of momentum as well. So here's Newton's second law. And so if we sort of think about the average net force, well, again, that's going to be mass times the average acceleration. And the average acceleration is nothing more than the change in velocity over change in time. And all I'm going to do is take this mass term and tuck it inside. So I'm left with the change in the quantity mass times velocity. Well, I know that that is the momentum. So you can see that really what Newton's second law is telling you about is it's telling you about how the net force changes the momentum over time. And again, we're only worried about the average force here so that we can keep things constant and keep these deltas rather than needing calculus and derivatives. But fundamentally what this means is that Newton's second law is really telling us that the net force acts to change your momentum with respect to time. So a change in either the magnitude or direction of an object's momentum, because again, this is a vector problem, requires an unbalanced net external force. So if this term over here, if the change in momentum isn't going to be zero, then that means this term over here also can't be zero. The other thing this tells us is that the net force and the change in momentum vector, the average net force and the change in momentum vector, always point in the same direction. So if you know the direction of the change in momentum vector, that means you also have to know the direction of the average net force. All right, so again, we've come back to really working Newton's second law problems when we're talking about momentum. And the last thing that we're going to do is basically we're going to say, well, what happens if I have multiple objects? Because what we'll see is there's a situation in which momentum will be conserved where we'll need to deal with the momentum of lots of pieces. So how do we calculate the linear momentum of a system of particles? So the easiest way to define it is just to say that the linear momentum of a system of particles is nothing more than the vector sum of the linear momentum of the individual particles. So the momentum of the system is nothing more than the momentum of particle A plus the momentum of particle B plus the momentum of particle C plus just keep adding on until you've included all your particles. And again, this is a vector equation. So there's an equation for what's going on in x. So the x component of the linear momentum of your system is equal to the x component of your linear momentum of particle A plus the x component of the linear momentum of particle B plus the x component of the linear momentum of particle C. And again, we know that we can calculate these individual linear momentums by taking mass times velocity. So the x component of the linear momentum of particle A is nothing more than the mass of particle A times the x component of particle A's velocity. And we repeat that for each particle that we've got. Again, this is the x equation. Obviously, I can get a y equation by basically playing exactly the same game. It's just now I want to add up the y components. So again, the y component of the linear momentum of my system is just going to be the mass of particle A times the y component of particle A's velocity, plus the mass of particle B times the y component of particle B's velocity, plus the mass of particle C times the y component of particle C's velocity, plus keep going until you've included all your particles. And again, since we live in a three-dimensional world, there's obviously a third equation for what's going on in the z direction. It works fundamentally the same way the first two do. So again, calculating the linear system, or the linear momentum of a system of particles, means that we just need to do the vector summation to add up the individual linear momentum of all the particles in our system.